Welcome back. In this lecture of power electronics, we will be discussing on the single phase half wave control rectifier with loads like the combination of the resistor and the source EMF and the combination of RLE, that is resistor, inductor and source of EMF. In the previous lecture, we have already introduced on this half control rectifier using the RL load. So this is the continuation from the previous lecture. The outline goes like this. We will be discussing on the firing angle analysis that has resulted for the transient current. So previous lecture we have seen that the presence of the inductor as the load result in the transient which is there in the waveform. So we will be analyzing that, and the half control converter with respect to this RL load, how it can be avoided with the help of the freewheeling diode. So that is our focus in this particular lecture. Together with this, we will be discussing two important load combination. One is the RE load, another is RLE load. So these two load analysis also we will be doing, and then we will summarize our this particular lecture. So we have seen that the firing angle is very important in case of the control rectifier. And what is the firing angle that need to be ensured so that no transient current is there? So firing angle to ensure no transient current is alpha is equal to tan inverse of omega L by R. Now we have the load combination which is resistor and the inductor. This omega is equal to 2 pi f, where f is the angular where omega is the angular frequency in radian per second and f is the frequency in hertz. The inductance is in Henry and the resistance is in ohm. So the combination of the load is RL. This angle corresponds to the load impedance angle. So we can say that the impedance Z is equal to R plus J times omega L. At this firing angle, the transient component becomes 0. So we will not get any transient if alpha is this value. On the other hand, if we need to find the maximum transient condition, then we have to put sine of alpha minus pi is equal to 1, which is equal to sine of 90, and that will give me the alpha to be equal to 90 plus phi, where phi is the phase angle which result from this RL load combination given by tan inverse of omega L by R. This represents the worst case scenario for the transient current, as this is the maximum transient current, and for practical implications avoid this firing angle for smooth operation. Now we will see how to avoid this transient condition. So again we will be taking the load which is RL load combination. The input that we give is basically single phase AC input with the mathematical relationship Vs is equal to 2 root 2V sine omega t, where V is the maximum amplitude of the AC sine wave. Here is the thyristor with the terminal anode, cathode and the gate. Now we have one more element that is connected in the circuit which is known as the freewheeling diode. Now what is the role of this freewheeling diode in the RL load condition? That is the topic of discussion, and together with the previous lecture, this lecture will complete the analysis on RL load with respect to the freewheeling diode. So again, the component, we have single phase AC source, we have a thyristor, we have RL load combination, and there is one more component which is the freewheeling diode. Now what is the purpose of this freewheeling diode? So the purpose is it will provide the path for the inductive current. Now you see, when the inductor will charge, then the current has to flow in the discharge path. So this diode will be activated, and the current or the energy which is present in the inductor will be discharging in this path of the freewheeling diode. It will improve the converter performance and it will reduce the voltage stress on the thyristor. So the thyristor, when is reversed biased, or the supply is the reverse bias condition, then in that case the stress that appears on the thyristor will not be there, because the energy which is present in the inductor now will be discharged through the freewheeling diode into the resistor. So the performance will be improved and voltage stress will be reduced. So let us discuss the mode of operation. So first we will discuss the discontinuous mode of operating principle. So this will be mode 1 thyristor conduction, where omega t lies between alpha and pi. So thyristor T1 will be forward biased in this case during the positive half cycle, and the triggering pulse will be applied at omega t is equal to alpha. So this is where the gate pulse is applied. Now the current will flow from the source to the thyristor to the load. In the mode 2 operation, where the freewheeling diode will be in conduction, so this will be ahead of this thyristor conduction. So it will start from pi and end with pi plus beta. Remember, in the previous lecture we have discussed that beta is the conduction angle in the case of the RL load combination. So here the input polarity will be reversing at omega t equal to pi. So the AC input will reverse at pi. Inductive current will continue to flow through the freewheeling diode. So that is the main purpose of putting the freewheeling diode in parallel with RL load, that the current which is present in the inductor now will be flowing through the freewheeling diode, and the current flow will be between the freewheeling diode and the load, and that will be decaying in nature. So current becomes zero at certain value of omega t, which is equal to pi plus beta. So here we can see in the discontinuous mode what is the waveform of the single phase half controlled converter with the load combination RL and also the freewheeling diode. So the input that we are giving is basically single phase AC supply with positive, negative, changing its value at pi, 2 pi and so on. We are giving the gate pulse at certain delay angle alpha, and this is the output voltage V0 and I0 that we get from the thyristor. So we can see here in the previous lecture we have discussed this beta, which is the conduction angle. This is what we don't need, because in the R load combination the thyristor will not supply any current, because there will be no inductor. But due to the inductor, the current will be there, energy will be stored, and the current will not decay even the voltage is not present. So voltage is not present, but even the current is present. So in order to avoid that, we will be using the freewheeling diode, and freewheeling diode will now can see it will be conducting from alpha to pi. So here the conduction process will stop. So if we do the discontinuous mode performance analysis, the average output voltage that we get V0 is equal to VDC, and given by the formula Vm by 2 pi 1 plus cos alpha. Average output current is, again, it is equal to V0 by R. So in the previous formula we have to divide it with the resistor value. Note here the Vm is nothing but root 2 times the maximum value, which is the peak input voltage. Output voltage is higher compared to without the freewheeling diode, and the current ripple is reduced due to the freewheeling action. So when we have the freewheeling diode, the ripple will be reduced. Now in the continuous mode of operation, when we discuss for the mode 1, which is again omega t from alpha to pi, thyristor T1 will be conducting, and the voltage equation will be root 2 V sin omega t will be the summation of the inductor voltage plus the resistor voltage. So this is what we have. The output current solution that we have is having the component in the steady state and the transient conditions. So we have both the steady state and the transient conditions. The load impedance is given by this formula, and the phase angle is given by tan inverse of omega L by R. I0 is the initial current at omega t equal to alpha. So what is I0? I0 being the initial current at omega t equal to alpha. Now in the second mode of the freewheeling diode, where the freewheeling diode is there between omega t lying between pi to 2 pi plus alpha, the voltage equation being having the zero value of the source, and this is what we have, the voltage of the inductor plus resistor. The current equation now becomes the value of I pi e to the power minus R by L omega t by pi. Now what is I pi? I pi is basically the current which is present at omega t equal to pi, that is the end of the mode 1. Current will decay exponentially with the time constant L by R, and the mode 2 will continues until the next firing angle at omega t is equal to 2 pi plus alpha. So here there is no input source. Again, when the firing angle will be given, the input will be there, and again the process will begin. So this is the continuous mode waveform of the converter with RL load and freewheeling diode. So here you can see the current I0 and the is changing, which is it is a continuous process of the current. And the next we give the gate pulse, and again we get the output voltage V0. So the rest remains the same except the freewheeling diode, which is having the conduction from beta to 2 pi plus alpha. So in the continuous mode of operation, we get a continuous current of I0. So what are the advantages of this freewheeling diode? Performance improvement will be there because we will be getting higher output voltage. So it will have better voltage utilization. Improved power factor will be there. So it will reduce the reactive power demand. Better current waveform will be there, and so it reduce the current ripple. Enhanced efficiency because the energy stored in the inductance will be referred to the load resistance again. Reduce voltage stress because the lower reverse voltage will be there across the thyristor. So if we summarize the key benefit, the stored magnetic energy in the inductance is effectively transferred to the resistive load during the freewheeling, and that will improve the overall converter efficiency. So in the RL load combination, when we don't have the freewheeling diode, a lot of energy was getting wasted. Now that energy which is present in the inductor will freewheel through the load, and as such we will be getting more efficiency of the converter. The next load combination that we will take is basically the RE load combination. So this is the single phase half wave controlled rectifier with the load, which is the combination of the resistor and the source of the EMF. The output voltage is appearing across the load. The load is carrying a current I0, and again we have the single phase AC supply given to the thyristor T1. So these applications of RE load combination generally is seen in the battery charging system, the DC motor drive, the electroplating process. Here we have the resistance, which is due to the internal resistance, and the EMF source, which is the battery voltage. The operating principle is the thyristor will be conducting only when the source voltage is greater than this battery voltage, and the current will flow only during the charging process. Now, if we see the operating condition, then the thyristor conduct when the input voltage is greater than the forward battery voltage, which is the forward bias condition. Gate pulse is applied again at omega t equal to alpha. So the natural conduction angle beta 1, now we will be having sine inverse of E by root 2 V. So it means that the source of the EMF will decide the conduction angle beta 1. So when the source of voltage is less than the battery voltage, then the thyristor is reverse bias and it will be turned off. The extinction angle beta 2 will be equal to pi minus beta 1 due to the symmetry process. The condition that we have for the conduction is alpha should always be less than beta 1 for the natural conduction process. So omega t, when lying between beta 1 to beta 2, then this is the charging current will flow, and the conduction period, we have the current I0 given by the expression root 2 V sine omega t minus the battery voltage by the resistor. Average charging current, which is the DC current, can be obtained by this expression where we are integrating from beta 1 to beta 2 the voltage that we have with d omega t. The power delivered to the battery can be obtained as the product of the battery voltage and the DC current. Power loss in the resistance can be obtained as I RMS square into R, and the rectifier efficiency is nothing but the ratio of the power output, which is the power delivered to the battery, by summation of the power loss and the power which is there in the battery. So output by input will have the rectifier efficiency. Now when alpha is greater than beta 1, this is the controlled operation, and the firing angle, if we see alpha greater than beta 1, the conduction period omega 2 will lie between alpha and beta 2. There will be reduced charging current and we will be getting lower average charging current. So the DC current now in this particular case can be estimated. Now we will be integrating from alpha to beta 2 for this particular voltage expression similar to the previous case, and the RMS current also we are obtaining between alpha and beta 2. So this integration that we do for alpha to beta 2, and this is the square of the voltage. Next load combination that we take is the RLE load combination. So RL is already present. With respect to that, we have a source of battery. So what happened in this type of load condition? So the load is having armature resistance or the internal resistance. In L stands for armature inductance of the circuit, and E is the back EMF or the counter EMF. So these type of primary applications generally come in the DC motor control. For armature circuit modeling, the battery charging process with series inductance, and electrochemical process having industrial applications. So RLE load make the most comprehensive load model for the practical applications. So most of the practical applications we will be seeing this RLE load combinations. Here the operating constraint that we have is that the minimum firing angle delta naught will again lie in the expression sine inverse of E by root 2V. So it is the battery voltage that is controlling this delta naught. So the constant alpha greater than equal to delta naught will have the thyristor conduction, and when alpha is less than delta naught, input voltage less than the battery voltage, thyristor will remain the off condition. Operating range, if we see, the minimum firing angle alpha minimum will be equal to delta naught, and maximum firing angle that we have is pi minus delta naught. Practical range of alpha will lie between delta naught and pi minus delta naught. Now, if you see the voltage equation, when omega t lies between alpha and beta, then the thyristor is conducting. We can write the equation root 2V sine omega t, which is the source, and this is the combination of all the voltages of the inductor, the resistor, and the source of EMF. Complete current solution I of t that we get is having the transient part as well as the steady state part, and the impedance will be under root of r square plus omega square, with the phi value can be estimated using 10 phi expressions. So current has both the steady state as well as transient component in this particular case. So if you see the performance parameters like the average charging current will be estimated using these expressions. So here both alpha and beta will be there, which is the cosine expressions, and the value of beta and alpha in terms of the battery voltage will also be there. So it has two terms in the average charging current. The average output voltage again will have a root 2V by 2 pi cos alpha minus cos beta minus the value which we have in the previous expressions plus the battery voltage. Here beta is the extinction angle when current becomes 0, and both voltage and current will depend on the conduction angle beta minus alpha. The control strategy is there, vary the alpha to control the average values. So average value will be controlled with respect to the alpha. So if we summarized what we have discussed is that, so there is no transient when alpha is equal to tan inverse of omega L by R, and maximum transient conditions occur when alpha equal to 90 plus phi, where phi is the phase angle of the load. We have discussed the load type characteristic with RL load plus the freewheeling diode, which is to improve the performance and have the continuous current. RE load will be occurring when we have the battery charging natural conduction constraint, and the load which is involving the RLE load, which is more comprehensive for DC motor control, combined effect will be there for the resistor, inductor, and the source of battery. In order to improve the performance, the freewheeling diode significantly improve the converter performance. Proper firing angle selection is important to minimize the transient condition. Load characteristic determine the operating constraint. So this completes our lecture discussion on two important load conditions, combining with the previous lecture where we have discussed RL load. Here we have discussed the other load types with the importance of the freewheeling diode. In the coming lecture, we will again take this discussion further with full control as well as semi converter. Thank you for now.